this is just a kind of formal way to say that all you have in this category are just those objects, these maps, and these maps satisfy these relations. Okay, and the second lemma, which again I'm not going to prove, which is kind of just a more detailed version of what I just wrote, is that any monotone function, say f from the n to the m, can be uniquely written as the following composition. So f is the composition of the several co-phase maps. Yeah, and since it's hard to kind of pay attention, well, sometimes this is kind of the most detailed notation, but in most of the computations people don't write this n, because you apply this to something, you usually know the object to which you apply this map, you know which n this is. So in this statement, since I don't want to compute this n's, I'll just skip this n's. So any function is just a composition of several functions. Well, we just essentially, you can take a map, you can kind of look at the image of this map and then embed this image of this map. This is kind of this decomposition to this and this part. And to make this unique, well, you need to say that you have some inequalities. So in this lemma, I assume that I have inequalities like this. So this is very easy to compute, but actually not that important for understanding of simplicial sets. Yeah, and also we can notice that m is equal to the n minus s plus r. Okay, so this is just the combinatorial stuff about this category delta. Now finally, definition of a simplicial set. So definition, let me define the category. So the category of simplicial sets, and I'm going to write this only once. Later, when I want to say simplicial set, I'm going just to abbreviate SS. So the category of simplicial sets, it's like a set, but with the little prefix s. So this is defined as the category of functors. Well, functors from the delta op to the sets. So this fun is notation for the category of functors, or maybe I'll write it somewhere. Maybe, well, I don't know. I think it's understandable, right? All the functors from the opposite category to the sets. So another way to say this, that this is all the pre-shifts on the category delta. Pre-shifts of sets. Okay, so of course, simplicial set X, this is just such a functor. And the maps are just natural transformation of simplicial of these functors, and it is very easy to verify that the natural transformation, so if, say, for example, if you have maybe f, so this is a map from x to y, right? So this is natural transformation x and y are in the simplicial sets. Well, this natural transformation is precisely the same thing as the fi that hits from the xi to the yi, right? So here, let me also add this additional notation that when I'm writing xi with this index I simply mean that this is functor x that I evaluate on the object I in brackets. Just a short annotation for this evaluation. So Fi is so this natural transformation is the same thing as this maps Fi for every I, right? So I is at least 0, commuting with simplicial operators. In particular, you can say that this thing commutes with this. Yeah, actually, for the simplicial operators, I can also introduce the following notation. So now the face map, right? So I'm going to use notation D with indices I and n. And this is by definition, you just take this functor x and evaluate this on the del ni. Right, so this was a map inside in the category. I apply a functor to this. This will be a map of the sets. So this is from the xn to the xn minus 1. So this is the face map of a simplicial set. And there's also the degeneracy map. Which is defined in a similar way. I'm going to use notation S for this map S and I. This is X that I compute on the codegeneracy map. And this is a map from the xn to the xn plus 1. So, if you prefer kind of this work with generators and relations instead of functors, we can interpret this definition in the following way. So there's kind of the diagram. If I take X to be a simplicial set, then there's a diagram for I have X0. Yeah, and also returning to this main definition, so objects of this Xi, so this is just some set, and objects of this set are called, this is I simplices of X. So objects here. So I have 0 simplices, x0. I have 1 simplices, x1. And I have x2 simplices, and then I have maps. So in this direction, from x1 to x0, there are two degeneracy maps, d0 and d1. I need to use the upper indices. But it's really annoying because sometimes people write I and sometimes n on the top, I on the bottom. So it's really annoying. So if I use my notation, so I guess this has to be upper 0 and 1 and lower 1. So this is the two degeneracy maps, the two face maps, and the degeneracy map between x0 and x1 goes in the other direction. So this is in the middle, and this is S00. Then if you look at what happens between x1 and x2, well, there are kind of now, well, people usually write it like this. So there are 5 maps. The face maps are now, so this is D2, 0. So then this is D2, 1 and D2, 2. Right? And the degeneracy maps are, so this is S1, 0, S1, 1, etc. So you can easily check that if you look at the xn, right? So that there will be n plus 1 maps going in one direction and n plus 1 maps going in the other direction. If you just count how many maps you have. Okay. So now maybe we can actually think about these maps geometrically. So for example, let's take, and also there's a terminology that 0 simplices are called vertices of X and one simplices are called edges of X. Yeah. For example, if you try to think naively about this, well, what's geometrically an n simplex, right? So 0 simplex is a point, 1 simplex is an interval, 2 simplex is a triangle, so 3 simplex is a tetrahedron, etc. So let's try to analyze, for example, what happens in the simplest possible case. So for example, if I want to think about this x1 as just the usual interval, right? So this is something that lives in x1, right? So for example, I can draw a picture, see, this is, well, I think from the elementary topology, you know what the simplicial complex is, right? So some picture like this with triangulation, maybe high dimensional triangulation. So if I use the geometrical intuition, right, and I want to understand these maps, for example, for pictures like this. If I have just one simplex, which is an interval, well, what would be the map, say, 0, 0? Well, I have vertices 0 and 1 here, and this map, this kind of takes the boundary opposite, or the kind of the simplex opposite to the vertex 0. So for example, if I apply map D, so this is D1, 0, right? So the opposite to the 0 vertex is 1. So this is give me just 1, right? And the other boundary map, or the face map, D1, 1, this gives me 0. So I have a simplex, and if you apply these face maps to the simplex, you kind of get faces, like in this case. Then in more a general situation, for example, you have two simplex, right? So then you have three face maps. So say this is 0, 1, 2. So then this map, so this is D2, and this is opposite to the vertex 2. So this is D2, 2. This gives me this one simplex. So this face map, this is opposite to the vertex 0. So this is 2, D2, 0. So this thing. And finally, since this is opposite to the vertex 1, this is D1. Okay, so this is, if you think about it geometrically, this is how this face maps acts. And you can, if you understand this picture, you can easily generalize this to any dimension. Now, how about the degeneracy? Well, the degeneracy is something that you don't see in the geometrical pictures like this one, right? Well, this is because, for example, let's look at the S00, 0, right? So, for example, I take 0. I think about this as some 0 simplex and x0. So S00 has to be a 1 simplex that lives here. And what is this? See, maybe I write it as before. So this will be a degenerate 2 simplex with 2 vertices 0. So these degeneracy maps, they kind of, if you have degeneracy map S with the index I, so you repeat vertex I twice. So for example, if you try to understand the next one, say S1, 0, right? So you start. So you start with some. You start with some simplex, 1 simplex, right? So let's draw 0, 1, and now, right? So I need to take this vertex 0, right? This is 0, and repeat this. So this will be a degenerate 2 simplex. 0, 0, 1. So this is something that you don't see in these geometrical pictures when you study simplicial complexes. You only see this in simplicial sets. Well, the reason is that the category, if you introduce this degenerate simplices, is much nicer. For example, it has this very short introduction as just the category of Pushout, right? Yeah, but the geometrical, or rather homotopy conformation is the same. So if you can model something with a simplicial complex, you can definitely model this with the simplicial set. And if you have a simplicial set, you can forget all the degeneracies. You don't see them on the pictures, and you get a picture for a simplicial complex. Okay, so this is basic. Yeah, and another basic terminology. Since we see that now there are some degenerate simplices, we can also say definition a simplex, so n simplex, which is just a point in the xn, is called degenerate if, well, I can find a simplex y in the xn minus 1 such that, well, the simplex and also say an index j, right, such that I can write this x as the degeneracy map for some degeneracy map applied to this y. So if you can describe a simplex as a result of applying a degeneracy map, this is called degenerate simplex. Well, if the simplex is not degenerate, this is called non-degenerate simplex. Right? Well, non-degenerate simplex if it is not degenerate. So we can separate kind of all the simplices into degenerate and non-degenerate ones. And of course, non-degenerate is kind of more important from the point of view of topology or geometry. But the degenerate are also here. Well, for example, why the category of simplicial complex is not very nice? Well, for example, you have a, say, map like this, and you want to collapse this to one simplex, right? This is, say, in the category of simplicial complexes. Well, this is a problem because you're collapsing this, and to describe the image, you need to have degenerate simplices. So it's not possible to describe a map like this if you don't have non-degenerate simplices. But on the other hand, if you have degenerate simplices, it means that, well, you kind of, if you have this picture, say you have, I don't know, if you want to describe this picture, right, you could say that something like, what's the cardinality? Well, you can describe just a very small amount of the simplices. For example, how many vertices I have? 5. And how many edges? Yes. And I'm assuming that this is also kind of included. So I also have this, right? And this is all information kind of you have. But when you have degenerate simplices, I can ask you, for example, a question. So let's take the following geometrical picture, right? So this is just a point, and I look at the corresponding simplicial set. What's the number of elements in nth component? Yes, it is always 1 for any n, right? Because you have, well, you have simplex like this, and so this is n equal to 0, right? Then you have n equal to 1, you have a degenerate simplex that looks like this. When n is equal to 2, you get a degenerate 2 simplex that looks like this, etc. So you see that when you can count the degenerate simplices, so kind of any simplicial set is automatically infinite. It has something in every component. Okay.
So retrieve the dimension of the simplex by looking at the symptotic stuff, this cardinality. This section.
So the dimension, if you want to define the dimension, you can say something like this. So what will be a dimension of a simplicial set? You just look at which, for each n, you have find the maximal n for which you have non-degenerate simplices. So here, for example, since all the simplices are degenerate, so the dimension of this still will be 0.
For n equal to, there's only one degenerate simplex for what x?
This is X that consists just of one point. Right. If this is one point, then you have just one point in each degree. Well, if you start with something more interesting, you'll get something more interesting in all the degrees. Yeah, and the simple remark, maybe I'll squeeze it here. So a map of simplicial sets is completely determined by the value of this map on non-degenerate simplices. I think it's a good idea maybe to introduce some notation. So let me say that the notation, I'm going to write xn degeneracy. This is subset in the xn of the, so subset of degenerate simplices, and then also xmg for non-degenerate simplices. So together these are just all simplices. So I can write that xn is a disjoint union of two sets, x degenerate n, this x non-degenerate n. And of course, if you know your map for non-degenerate simplices, every degenerate simplex you obtain as is applying potentially several s's like this, and the map commutes with such s's, you know everything for this map. Okay. No. So you're asking that is it true that degenerate or non-degenerate, if you kind of take the say degenerate simplices in each degree, is that this simplicial subobject? No, it's not. This is just a decomposition of a set in for each n. Okay. So then the simplest possible simplicial set is a discrete simplicial set. So a simplicial set is called discrete if all its simplicial operators are bijections. Well, for example, another way to say this is the following. You can take the functor, so it has several notations, but I use the shortest one. So the functor C, so C for constant, from the sets to the simplicial sets. Right? It just takes takes a set and sends this to the simplicial set C of S. And if I want to look at the degree n part, so n simplices, then this will be just S. And all the simplicial operators are, so simplicial operators are bijections. So in this sense, you can consider this full subcategory of discrete simplicial sets, and this is just kind of the same thing as the equivalent to the image of this functor. So sets is a full subcategory inside simplicial sets. But what interesting about this functor, that this functor has a left and right adjoint. So the left adjoint is called P0, and the right adjoint is much easier. This is just taking the zero simplices of the set. Right? So in other words, if I want to understand this adjunction, I need to understand that the home in the category of simplicial sets between some discrete simplicial set generated by the S and some simplicial set X, this is in bijection with the home in the category of the sets between S and x0. So if you think about this, you'll find immediately this is quite obvious. Well, define pi 0, well, just a little bit more complicated. Well, I need to, I need to do this in 2 steps. Well, for a simplicial set X, consider the binary relation. I'm going to write this for equivalence with 1. So binary relation on x0. Well, by definition, this is x. So what some vertex, say little x, is equivalent to another vertex y using this binary relation. So that here x and y lives in the x0. So if there is an edge E in the x1, well, let me just draw this as a picture. So there is an edge that connects x and y. So you can see that this is not necessarily symmetric or transitive. This is of course reflexive, because you have a degenerate one simplex xx for any x. But we can take kind of the smallest equivalence relation that contains this. So generate the equivalence relation from this binary relation that we just introduced. Well, in other words, this is just kind of you have 2 points, 2 zero simplices, and you have a zigzag in one direction, in another direction. Then this is an equivalence relation that I'm talking about here, right? So then we get a equivalence relation, and we define equivalence. Maybe just write simple tilde for this equivalence relation, and then pi 0 of x is by definition you take x0, so the equivalence classes modulo this equivalence relation. Well, you can also write this as follows. This is equalizer of the 2 maps. So d0 and d1 from x1 to the x0. So the answer for this p0, this only depends on the x0 and x1. Yeah, and then let me use this as a little exercise. So lemma that the pi 0 is the left adjoint to the functor C. With this definition, it's not very hard to prove this. Okay, so the next definition.
How does pi 0 act
on the morphisms? Well, for example, this definition is completely kind of canonical and categorical. So you can use this to extend this to morphisms.
That's a question. We call it the breaker, the image of the morphisms in the delta category.
Yes. Well, in the delta category, you can also call, well, you can call them maybe co-simplicial operators.
Okay,
So.
yeah,
Yeah, so I want to define the standard simplex. Standard n simplex. Well, from the point of view of the pressures, it's very easy to define. So delta n, this is precisely the main representable functor. So quite often people use notation h like this. So main representable functor with the object n, but this is just means that we consider functor home in the category delta blank n in brackets. So this is kind of the contravariant functor presented by the object n. So, for example, if I take this standard simplex and try to understand what I have in the degree m, or what are the m simplices of this thing, then this is, just by definition, will be a home in the category delta between M and N. No. No. Just oh, there's any h that you can write, which is by definition just this thing. Okay. Yeah. Let's compute home in the category of the simplicial sets from the standard and simplex, well, to some simplicial set X. So what's the answer for this? Yeah, the answer is yes. So by Unada's lemma, right? So since this is a representable functor, this is Unada. You're supposed to compute this on the object that representing this functor, but this is what we define to be X. So this instead of the way to think about the n simplices, so you can say that X is in the Xn, or equivalently, quite often I will saying that the X is just an arrow from the delta n to the X. So that's the Unada's lemma. So, and what is the home in the category of simplicial sets between delta m and delta m? Well, just a special case of the previous computation, so we apply Unada's lemma and see that this is home in the category delta from n to m. Okay, so this is basically all the main terminology. Now let's notice also one simple lemma. So the category of simplicial sets is bicomplete. Right? So bicomplete means that it has all the limits and all colimits, and this is not really specific for the simplicial sets. So this is true for any category of presheaves. So for example, we have delta 0, this is the terminal object. Right, so then we have empty set, this is initial object, right? So this empty set is a functor that takes n, and the value on this of n is just an empty set, so this is for any n. So this is initial. And in fact, you can easily see that if, for example, you want to compute products or co-products, you just do this component-wise. And the same for, say, pullbacks, pushouts. So a very simple theory of limits and colimits here. So next, again, simple observation that works for any presheaf is that any simplicial set X can be presented as a colimit of the standard simplices. So, well, any simplicial set has presentation like this. X is the colimit delta n over the category of elements of X. Again, there is nothing specific about simplicial sets here. This is true for any category of presheaves. The category of elements of the simplicial set. So again, this is general, it makes sense for any presheaf, and it's defined as follows. So if I look at the X from the delta to the sets, okay, so that's a presheaf, then the elements of this large X, well, this is just the objects, well, has objects which are pairs. So I have an object in the category delta, and then I have x, little x, so this m is in delta, and this little x is in the xn. And the morphisms, so f, which is a map from the pair n x to the pair m y. So f is the map in the category delta from the n to the m. And additionally, when I look at what this map on the simplicial set is doing with the y, this is point x.
Можно спросить, не правда, что это типа симплициальная замена категории?
Я не знаю, что такое симплициальная замена категорий. Это то, что называется категория элементов. Это то, что называется обычной категорией элементов. Ну, это в том смысле, что ну, как бы это типа направлений теории стеков. Да? То есть вы можете взять функтор со значениями множеств на какой-то категории, а можете вместо этого смотреть как бы на фибрацию категорий. But anyway, that's a formal definition, and Unada's lemma also allow us to interpret this as follows. So the objects, so by Unada objects, this is the same thing as the diagrams like this, and the morphisms, well, are just, so we have one object, little x, you have another object with m and little y, and the morphism, well, is just map f, the same as before, making this triangle commutative. So here this is the home in the category delta is f. So these are morphisms in this category. It's just Unada's interpretation of the same thing. And you can use this as a very simple exercise in category theory, that whenever you have a category, so if you take any category, delta or any other, say, small category, then if you consider presheaf of this category, then any presheaf is a colimit of representable presheafs. Yeah, this is all. Thank you. Okay. Okay, so then I have lemma, and this is maybe a little bit less trivial. So I'm going to ask to prove this lemma on the first assignment. So this states that any n simplex of x, so n simplex of x, again, I think about this as a map, so from the delta m to the s. So can be uniquely factored in the following way. I have delta m, then there is delta m in the middle, and then there is map to the s. So let's call the first map alpha, the second map tau. So in this unique factorization, alpha corresponds to a surjective map n to the m, and this tau, this is a non-degenerate simplex. So non-degenerate m simplex. If you think about this, it's kind of clear, right? So whenever you have a simplex, well, it's kind of, after some steps, this is image of some non-degenerate simplex, and you can, if you work a little bit further, you can solve that there is a unique way to do this. S is a simplicial set. So this one, sorry. any n simplex of S. Okay, so now with this lemma, I want to define the skeletal filtration. So definition, if I take, now I'm switching my notation to the S. So if I take S to be a simplicial set, then I can define the simplicial sub-object called the case skeleton of S. So this is simplicial sub-object. Or simplicial subset, well, such that if I look at the skeleton at the level K of the set S, right, so look at the n simplices of this thing. So this thing consists of n simplices so admitting a factorization like this. So I have, so n simplex is a map from the delta n to the S. I can factor it through some delta m. And in this factorization, I want to assume that m is less or equal than k. So this is tau, and this is alpha. So that's a formal definition, but if you want to think about this informally, so the following remark will give you the answer. So the skeleton of level k of S is the smallest simplicial subset containing all non-degenerate simplices of dimension less or equal than p. So this is what it's more or less.
And is there some conditional alpha and tau?
No, you can take the factorization that exists from this lemma.
Exists for any n.
Yeah, and I take a simplex. For this simplex, there is a factorization, and now I assume that this m in the middle is bounded by that k. Well, quite clearly, you see that skeleton with the index k minus 1 is contained in the skeleton with the index k, right? And for example, again, by the previous lemma, you can notice that any simplicial set is just the union of its skeletons. What's not the same? Now the skeleton is something like this. For example, this is just a 2 simplex, right? So the sk, so this is x geometrically again. So the skx, this is these 3 vertices, right? So and here I'm including this 2 simplex. So the skeleton sk1 of x, this will be this triangle, but I don't include this, these 2 simplex. So this is just 3 1 simplices here. And the skeleton 2x, well, in this case, this is just coincides with the x. So sometimes what we constructed is called the skeletal filtration of a simplicial set. So maybe let me write here. the skeletal filtration of the simplicial set.
So the skeleton can be
Well, as any simplicial set, it contains degenerate simplices, of course. Like for example, in this case, you have 3 vertices, so it means that in any degree you have 3 points. Okay. So now I want to define a boundary of a standard simplex. Well, for example, by looking at the previous picture, it's natural to define this to be a skeleton with the index n minus 1 of the standard simplex delta n. So that's the definition of the boundary of the standard simplex. But if you want to understand more what boundary is, you can write the following formula. You take the boundary of the standard simplex, and if you're trying to understand the m simplices of this, then this will be precisely the same thing. Well, we just kind of unwind the definition. So these are maps alpha and the home delta from m to m, such that alpha is not surjective. So you can also take this as a definition of the boundary. Right, so it makes sense, right? Because if you have surjective, then you get the whole simplex. Okay. Yeah, and you can also notice that if you, for example, take some simplex, so say sigma, and this will be a non-degenerate non-degenerate k-simplex. So then you can take the sigma, right? So you can think about the sigma as a map from the delta m to the s. And then you can restrict this sigma to the boundary of the standard simplex. And then, of course, this is contained in the skeleton with index k minus 1 of the s. So I'm going to use these maps to formulate the next proposition. So proposition. So the following square. So where here I have the coproduct of the boundaries of the standard simplices, and the coproduct is taken over all non-degenerate simplices, so some simplicial set S. So I have a simplicial set S, I have a set of non-degenerate simplices in degree k, and I take a coproduct of all the boundaries. So this is mapped to the coproduct over the same non-degenerate simplices, k-simplices. Right, so this is just the inclusion of the boundary, right? So this boundary is included in the standard simplex k, delta k. So then this thing, by the previous observation, this is mapped to the skeleton with the index k minus 1. Right? And then you can look at this diagram and take the Pushout in the category of simplicial sets. So then the claim is that you get the skeleton of the S, but with the index k. So the following square is a Pushout. Okay. So maybe we can discuss briefly what the proof is. Right, so what you really need to check that to say that this is a push-out, can we reformulate the problem? So this will be, so what we want to show, to prove this, that if you take any simplex, now let me call this tau, so this will be a simplex in the skeleton with index k of the S, but this is not the simplex in the skeleton k minus 1 of the S. So they want to show that any such tau factors uniquely in the following way. So this is delta n mapped to the delta k mapped to the S. So let me call this again alpha and sigma. So where sigma is a non-degenerate simplex, so non-degenerate k simplex, and alpha doesn't factor through the boundary. Okay. So at the end. Yes, thank you. Right. So I'm just kind of formulated the statement that this is a push-out, right? If this is a push-out, if you just look at the definition of push-out, and here you can, since they can do this component-wise, in this category of simplicial sets, this is what you get. So to say this is push-out is to say that you have this property, right? But the lemma that was here, that I erased, states that actually I have this, so by previous lemma, tau has factorization right, so delta n is mapped to the delta m, and this is mapped to the S. So this is by the lemma that I left as an exercise, and I promised that this exercise will be on the first assignment, right? So the only difference here is that m is not necessarily k, right? But we can easily observe the following. So since simplex tau that we consider is contained in the skeleton k, this implies immediately that the m is less or equal than k. And since tau is not contained in the skeleton with the index k minus 1, right? So this implies that we have inequality in the other direction. And that's what we need to show. Okay, so I have only several minutes left, so I want to start.
Sorry, I have a question.
Hmm?
Why do we need sigma to be non-degenerate for the middle board?
Here?
No.
Otherwise, it would be in as k minus 1.
No, we say that the boundary is k minus 1 skeleton, but it should be true for any simplex, not only non-degenerate. Isn't that right?
I'm not as sure where you refer.
Middle board.
Here?
Yeah. Why do we need sigma to be non-degenerate?
Well, no, I'm just explaining how I get this diagram. So here I have non-degenerate simplices.
But then you're looking to be non-degenerate.
No. So this kind of proper explanation that I use for the proposition. Yeah, so let me just say maybe several sentences about the second section. So this is called the geometric realization. Сколько? Ну и хорошо. So we can define the so-called standard topological simplex. So I'm going to write this delta n top And this will be by definition, so points, so n points in the Rn to plus 1, and all the coordinates are non-negative, right? So satisfying the condition that the sum of the xi's is equal to 1. I'm pretty sure that this is a definition that you've seen before, right? So this is standard simplex that you realized in the n-dimensional space, right? But you can think about this if you want as the, so this n top, this is a map from the delta, so sorry, not a map, functor, to the delta, from the delta to the topological spaces, right? On objects, this gives you this delta n top, and there's clear map. You can realize any map in the delta by the map of such simplices. So this is a cosimplicial. Right, before we defined only simplicial objects, right, and we wrote op here. If you don't write op, this is called cosimplicial object. Cosimplicial topological space. Of course, we only interested in simplicial sets actually, but you can define simplicial and cosimplicial objects in any category. So that's a cosimplicial object in the category of topological spaces. So the geometric realization of X, which is a simplicial set, has the following notation, and this is by definition just the tensor product of X over delta with the delta top. So let me finish here with a very simple definition. So in the beginning of the next lecture, I'm going to explain how to think about this. But whenever you have kind of a diagram, right? You have a category D that parameterizes this diagram. You have if you have a functor from the D to the category, and you have a functor from the D opposite to the category, you can define a tensor product of functors. So that's an instance of a tensor product of a functor. So next lecture I will start maybe with adding a little bit more detail on this definition.